Now that we've walked through the theory of eigenbases and diagonalization, let's have a go at a simple 2D example where we can see the answer graphically, so we'll know whether or not our method has worked as expected. Consider the transformation matrix T equals 1, 1, 0, 2. Hopefully, you'd feel fairly comfortable at this point in drawing the transformed square and vectors that were used in the previous examples. As the first column is just 1, 0, this means that our I hat vector will be unchanged. However, the second column tells us that j hat, the second vector, will be moving to the point 1, 2. Let's also consider the orange diagonal vector to point 1, 1. Multiplying through gives us 1, 1, 0, 2 multiplied by 1, 1. So thinking about rows times cols, we're going to get 1 plus 1 and 0 plus 2, which gives us 2, 2. It's interesting to consider that this particular transform could be decomposed into a vertical scaling by a factor of 2, and then a horizontal shear by a half step. Because we've chosen such a simple transformation, hopefully you've already spotted the eigenvectors and can state their eigenvalues. These are, at lambda equals 1, our eigenvector is 1, 0, and at lambda equals 2, our eigenvector equals 1, 1. Now let's consider what happens to the vector minus 1, 1 when we apply t. So, 1, 1, 0, 2 applied to minus 1, 1. This time is going to equal rows times cols minus 1 plus 1 and 0 plus 2, which equals 0, 2. And if we apply t again, we're going to get the following. 1, 1, 0, 2 applied to 0, 2, which is going to equal rows times cols again, 0 plus 2 and 0 plus 4. So this thing finally is going to equal 2, 4. Now instead, if we were to start by finding t squared, so t squared is going to equal this matrix multiplied by itself. So applying rows times cols, we're going to get 1 times 1 times 1 times 0, so that's 1. Rows times cols here, we're going to get a 3. Rows times cols here, we're going to get a 0. Rows times cols here, we're going to get a 4. Now we can apply this to our vector and see if we get the same result. So 1, 3, 0, 4 multiplied by minus 1, 1 is going to equal rows times cols, so we're going to get minus 1 plus 3 and 0 plus 4, which of course equals 2, 4. We can now try this whole process again, but using our eigenbasis approach. We've already built our conversion matrix C from our eigenvectors. So C is going to equal 1, 0, 1, 1. But we're now going to have to find its inverse. However, because we've picked such a simple 2 by 2 example, it's possible just to write this inverse down directly by considering that C would just be a horizontal shear one step to the right, so C inverse must just be this same shift back to the left again. So C inverse is going to equal 1 minus 1, 0, 1. It's worth noting that despite how easy this was, I would still always feed this to the computer instead of risking making silly mistakes. We can now construct our problem. So t squared is going to equal c d squared c inverse, which of course in our case is going to equal 1, 1, 0, 1 multiplied by our diagonal matrix, which is going to be 1 and 2, and that's all squared, multiplied by c inverse, which is 1 minus 1, 0, 1. Working this through, we can see that, let's keep this first matrix, 1, 1, 0, 1, and work out this bit. So we'll say, okay, this is going to be 1 and 4, on the diagonal. 1 minus 1, 0, 1. And let's work out these two matrices here. So we've got 1, 1, 0, 1 multiplied by, so we're doing rows times columns in each case. So for example, 1, 0 times 1, 0, we get a 1 here. We're going to do the second row in the first column, we get a 0 there. First row and second column, we're going to get a minus 1 there. And the second row and the second column, we're going to get a 4 here. Okay, and then working it through one more step, we're going to see that we get more grinding. We get first row, first column, 1. Second row, first column, 0. First row, second column is 3. And second row, second column is 4. And applying this to the vector minus 1, 1, we're going to get something like this. So 1, 3, 0, 4 applied to minus 1, 1 is going to be rows times cols. So minus 1 plus 3 and 0 plus 4, which equals 2, 4, which pleasingly enough is the same result as we found before. Now, there is a sense in which, for much of mathematics, once you're sure that you've really understood a concept, then because of computers, you may never have to do this again by hand. However, it is still good to work through a couple of examples on your own, just to be absolutely sure that you get it. There are, of course, many aspects of eigentheory that we haven't covered in this short video series, including undiagonizable matrices and complex eigenvectors. However, if you are comfortable with the core topics that we've discussed, then you're already in great shape. In the next video, we're going to be looking at a real-world application of eigentheory to finish off this linear algebra course. This is a particularly famous application which requires abstraction away from the sort of geometric interpretations that we've been using so far, which means that you'll be taking the plunge and just trusting the maths. See you then.